Before I get too far into this section, let me just mention something I didn't mention with ellipses. A circle is actually a special ellipse where the denominator of both terms are just 1. So like x squared plus y squared equals 1 would be an ellipse. Would be an ellipse where the semi-major and semi-minor axes would be the same length. So basically it would simply be a circle with a radius of 1. And so therefore that's something I probably should have mentioned in the last section. Okay, now in this section we're going to start with hyperbolas and describe hyperbolas, and then we'll move on and talk a little more about things not centered at the origin. Well, hyperbolas have foci as well, but the difference between the ellipse and the hyperbola, well, the ellipse, remember, had those 2 points called the foci. The distances from those foci to the a point on the ellipse, their sum was always a fixed value. But for a hyperbola, those distances from those 2 fixed points, their difference is actually going to be a fixed value. So therefore it's a little bit harder to follow, but I'll try to draw you a picture down here with a hyperbola and explain it for you. So what we're saying here with hyperbolas, this point right here is the foci, so that would be your F1, and over here is another foci, F2. Well, let's look at the red lines. If you went from this foci to a point on the hyperbola, and then went from that point to the other foci, well, if you took the length of this piece minus the length of this piece, you would get a constant. Let's call it K. Well, it turns out if you pick another point on the hyperbola, say this point up here, and you found the distance from this foci to that point, and then found the distance from this foci to that point, and you took the length of this segment minus the length of this segment, you would get exactly the same value as you got before. So that's what they mean when they say up here, the distances from the 2 fixed points in the plane have a constant difference. And so hopefully that helps you understand what that statement means. Now, with a hyperbola, we need to talk about the focal axis, the center, and the vertices. Okay, so let's take a look at a couple centered at the origin. Now the difference in the formula, you'll notice we have is a difference, and so pun intended there. So instead of a sum, we have a difference. So if you have x squared over a squared minus y squared over b squared equal 1, okay, then to find the center to the focus, it would actually be c equals the square root of a squared plus b squared. So it's going to be the same in both cases, whether the foci is on the x-axis or the y-axis, the center of the focus is going to be c. But the actual foci, when it's centered on the x-axis, is going to be the points plus or minus c0, whereas if it's centered on the y-axis, it's going to be the points 0 plus or minus c. And the vertices, when it's centered on the x-axis, are going to be the points plus or minus a0, and when it's centered on the y-axis, the vertices are going to be the points 0 plus or minus a. And so, and actually the asymptotes can be determined by setting this side equal to 0 and solving it, and if you solve it, you get slant asymptotes of y equal plus or minus b over a, and if the foci is on the y-axis, you get slant asymptotes of plus or minus a over b x. So either way, so again, slant asymptotes here are plus or minus b over ax, and slant asymptotes over here are y equal plus or minus a over bx. Okay, so let's go ahead and tackle one. Okay, let's do one where we have the x squared term minus the y squared term. So this one has x squared over 9 minus y squared over 4. So the square root of 9 is 3, so we'll say a is 3, and the square root of 4 is 2, so b is 2. So based on this formula up here, the center to the focus would be square root of a squared plus b squared, which would be square root of 9 plus 4, or square root of 13. So the foci would be plus or minus square root of 13, 0. And if you go back and look, that point here is minus square root of 13, 0. And then this point here is plus square root of 13, 0. Okay? And then the vertices of the hyperbola are the points plus or minus a0, so that would be plus or minus 3, 0. So here's the vertex on the left, minus 3, 0, and there's the vertex on the right, 3, 0. Now, let me clean up some of this, get some of this stuff out of the way here. Now, these two lines here, these two are the slant asymptotes, because remember the slant asymptotes would be plus or minus b over ax. Well, b is 2, a is 3, so it's plus or minus 2/3 x. So this line here is y equal 2/3 x, and this line here, over here, is y equals minus 2/3 x. And notice that as x gets larger or smaller, notice how the graph of the parabola tends to get closer and closer to the lines. So you can see that those are actually slant asymptotes. So now let's look at one where the foci are on the y-axis. Well, that would mean that I have a y-squared term minus an x-squared term. And so in this case, a would be the square root of the denominator of y squared, which would be 2, and b would be the square root of the denominator of the x squared term, so it would be 1. Well, you get the center to the focus the same way. You just take c equals the square root of 4 plus 1, a squared plus b squared, so that would be square root of 5. But this time the foci is on the y-axis, so it would be the points 0 plus or minus square root of 5, and the vertices would be on the y-axis, so that would be the points 0 plus or minus a, which is 0 plus or minus 2. And so here's one focus right here, and that's 0 minus square root of 2. The other one's hidden behind this point right here, but it's 0 plus square root of 5. Okay, so this is 0 minus square root of 5, and up here you have 1, 0 plus square root of 5. And then the vertices are 0, 2, and 0, negative 2. And then in order to get the asymptotes, which actually helps you draw it, you would have y equals plus or minus a over bx, so that would be 2 over 1x, which would just be y equal plus or minus 2x. So this slant asymptote is y equal 2x, and then this slant asymptote, I'll label it down here, is y equal minus 2x. And so that's your slant asymptote. There's a practice problem here that you can try, and the answers are given below it. Now, I went ahead and gave you a note about circles. A circle is simply an ellipse where a and b are the same. So I didn't describe it exactly like that a minute ago, but if you had x squared over 9 plus y squared over 9, well, you could actually multiply everything by 9 and get the standard form for the equation of a circle, and see that that's simply a circle centered at 0, 0 with radius 3. And then, of course, if it's not centered at the origin, you shift the values appropriately. Now, if we took basically an ellipse that we had earlier, and since I've already talked about this, I won't spend a lot of time on it, but basically we would simply take the ellipse we had earlier. I think we had ellipse x squared over 9 plus y squared over 4, and basically we would shift this. This is the earlier ellipse, and so we would shift this 3 to the right and 4 units down. So from x minus 3 we'd shift it to the right, and y plus 4 we would shift it down 4 units. And so basically we would take that ellipse and shift it over 3 and down 4, and so the center would be at 3, negative 4, and then all of these values would get shifted 3 to the right and 4 down. And you can see the new values you would get if you took those values and shifted them 3 to the right and 4 down. Okay, let's go back to our hyperbola that we did that was on the y-axis, and remember that looked like this, but that was for y squared over 4 minus x squared over 1 equal 1. But if we replace y with y plus 2 and x with x minus 1, well, that means to get the new hyperbola for the x value, we'd have to shift it to the right 1 unit, and to get the new y values, we'd have to shift it down 2 units. So basically, I'm going to take this hyperbola, and I'm going to shift it down 2 units and to the right 1 unit to get the new points of the hyperbola. And so that's basically how you basically just, you can get the conic equations. You can graph the conics that are centered at the origin, and then you can take those conics and shift them however many units you need on the y and the x-axis to get the new conic section, or the graph of the new conic section. So it's not that difficult if you understand the basic graphs of the ones that are centered at the origin. And that pretty much ends the discussion on conic sections, but I still have to talk about polar equations coming up.